Okay, so our next speaker is Matthew from Bloomberg, who's going to be talking about lowering Rocq into C++.
Yeah, so this is a joint work with Joomy, and also I realized this morning that with Ariel, the three of us round out all of Andrew Appel's 2024 students. So we have a theme this morning. So in this room, I think there is one thing that we could all pretty easily agree on, and that is bugs are bad. Maybe there's the alternate argument that could be made because bugs also give us fun problems to study, but at least in code, bugs are bad. And a second thing that shouldn't be too controversial here is testing is great, but it's not enough. So as one example, at Bloomberg, in an implementation of concurrent hash tables, here we see a commit where a bug was found because tests are in particular weak at finding bugs that arise from concurrency, because concurrency results in non-deterministic behavior, and it's impossible to actually test their absence, and thus we need stronger methods if we want to prove or guarantee the absence of bugs in concurrent code. And in this case, this line of code caused a data race where there was two threads trying to access the same location in memory. So as one solution to this problem, Joomy and I are presenting Crane, which is a new tool where we extract Rocq to C++, and our approach is to generate functional style, memory safe, thread safe, and readable C++ code. And also, this is very much still under active development, but we at least have the basics up and running, so we can talk about it. So why did we choose C++? Well, at Bloomberg, C++ is the primary programming language used, and because we actually want to get to the point of having verified code in production, it makes the most sense to meet engineers where they are and try to work with them instead of imposing as many changes as we might want to theoretically. So it's a pragmatic choice and very practical. Also works with existing code bases. And along those lines, we also strive to generate code that's readable and looks relatively normal, so it's not so scary to the random engineer who maybe doesn't know about Rocq or verification. They can still potentially interact with code that was generated by our tool. Also, one thing we learned while developing this is that C++ actually has a relatively large number of functional features, making it a relatively natural target when extracting Rocq. But it still is a kind of systems-level language that allows for low-level optimizations when necessary. And so it kind of acts as a portable assembly language, combining the best of both a low-level language, but also some functional aspects. So it's been kind of a surprisingly nice language to target for Rocq. So having said that, what does functional style C++ look like? What is the code that we extract? So to start with, let's look at an inductive data type, lists. So how do we write this or translate this into C++? Well, we end up with this. A lot of code. Looks like C++, maybe a bit scary, but if we look at the individual pieces, it actually makes some sense and lines up. So first, let's look at the nil constructor. When extracting C++, all of our constructors become structs in C++. So if we look here, we have a struct that we call nil. It has a template argument, which basically says it's parameterized by some arbitrary C++ type. And this struct doesn't actually contain any data, because as we'd expect from Rocq, nil doesn't contain any parameters. But we do associate with it a constructor make, so we can make empty things. And then for the cons constructor, again, we end up with another struct. This time we call it cons. But it actually does contain data. So it contains an element of A, or in this case, really the type that would correspond to what A was. Also has a pointer to another list, and again, a constructor. And lastly, the actual type itself, list, is translated this thing called a variant in C++, which, and if you're not familiar with that, it's really just a coproduct. So the list type is the kind of things that are either nils or cons. And altogether, what we end up with is list is extracted to a relatively normal-looking implementation of a linked list in C++, which is really what it should be. And now, what about a function? How would we extract the map function? Or I guess, do we? Well, again, a relatively, more verbose program in C++, but it also carries the same structure as the original Rocq code. So, looking first at its type, more verbose, but it takes, basically it takes some function from two types that are given as template arguments and a list, and it returns a list of type A and returns a list of type B. So everything is still kind of preserved, relatively speaking, to what it was originally in Rocq. And now we have pattern matching as the kind of core structural element of this function. And this is doable in C++. Again, syntactically, it's quite different, but we have this thing called the visit overloaded pattern. And it really does correspond precisely with match. And yeah, so we see visit overloaded, and some stuff we'll go over in a second. And then we apply that thing to our argument L. And yeah, it's the same as a match L. Now looking at each case, the visit overloaded pattern basically takes C++ lambdas, and they act as the case arguments for each branch. And so for the nil branch, nil goes to nil. And if we look at the C++, we have this lambda that takes a nil of type of list A, or a nil A struct, really, and returns the nil B struct, which there's only one because they're empty. And in the case of cons, we have this second lambda that takes some arbitrary cons A struct in C++ and builds a cons B struct by applying f to the argument contained in the cons B struct, the term itself, and then recursively calling the function on the tail of the linked list. So, at first it looks pretty different, but at the same time, we're really able to match the precise syntactic structure modulo very different concrete syntax. Having said all that, we also want the ability to customize extraction and to represent things so they look a bit more natural in C++. So, because we also do this as a fork of the standard OCaml extraction, we kind of take the same approach and allow users of our extractor to provide custom things, like custom ways to extract any term in Rocq. So as an example, in Rocq, cat is the name of string concatenation. And if we want to, if we end up extracting strings in Rocq to strings in C++, we might also then want to change how we need to change how we represent the string concatenation. And we do that by this command inside of Rocq. And if we look at it, we have this %A0, which is just a kind of macro thing that represents the first argument, %A1 that represents the second argument, and then when we actually extract cat of two strings, it'll then become the first string plus the second string in the C++ file. And we can also specify at the end a library where that we may need to import in the file in order for this syntax to work. So in this case, it'll add the import string in the kind of top of the C++ file. And similarly, we also allow users to customize how inductive types are extracted. And in the case of bool, it looks like this, where we provide the name of the type in C++ corresponding to the Rocq type. We give the names of the constructors, the representations of the constructors. And also we give the representation of the pattern matching. And in this case, we have to, again, have these macros to account for where all these things are placed. So as we want pattern matching on bools to become if statements in C++, we use an if statement, and we kind of are able to say, place the scrutiny in the syntax in C++ by %scrut. And we have %br0, which it says where to place the body of the first branch, and %br1, where to place the body of the second branch. And with this, yeah, our bools actually match to C++ bools, and it works out pretty nicely. And lastly, we also provide a way to support monadic effects and extract them in a relatively natural way, well, in C++. Because as most of us know, Rocq is a purely functional language, and that means it has no actual effects. So we don't have I/O or state or concurrency. And given my original example, you think we'd probably want to talk about that, and indeed we do. Rocq is just functions manipulating values, and in functional programming, we can use monads to represent effectful computation. And indeed, that's doable in Rocq, and that's what we do here. And to then support actually having those computations occur in the extracted code, we provide an abstract interface that allows users to specify both the functional interface for their monadic effects and also then how those things that in the interface are actually represented in the C++ files in extraction. And in our case, we plan on using iTrees to represent all of our effects because they're a very common and useful way to write proofs about effectful code. But that is a choice, and our interface works for any kind of monadic effect itself. So to show how this all works, we'll look at a very simple example we're familiar with, I/O. So when working with I/O in an iTree setting, you first define a type family containing all the operations of the effect. And then to make it into a monad, we derive the actual monadic interface using the iTree infrastructure. And then, when it comes to the extraction side of things, we tell Crane that I/O is a monad. And we also specify how each operation should be extracted in C++. Having done all that, we can then write a monadic function inside of Rocq, as one would always do, like typical, normal. And in extraction, it actually extracts the C++ looking like the function you would expect without any, directly. And yeah, works out quite nicely. So the last thing, we're particularly interested in verifying concurrent code because concurrency is hard. And so why is it hard? In general, there's three approaches we're going to talk about with concurrency. If you do fully uncontrolled concurrency, you could have multiple threads accessing the same part of memory, and you could have data races, and it's just very likely to have bugs. And so that's not a particularly good approach. You could use locks. And so when using locks, threads kind of each uniquely claim access to shared memory, which guarantees the lack of data races. But threads can be waiting to get access to a location in memory. You could have states where the code gets stuck because every thread is waiting for some piece of memory and none of them can continue to progress forward. And also, this approach doesn't compose horizontally as you add threads. So our approach that we plan on using is software transactional memory. So in this approach, each thread computes optimistically, and before committing an actual change to shared memory, make sure that nothing else happened that affected the shared memory, and if so, it retries. But with this approach, it's composable, there's no data races, there's no deadlocks, and there's no waiting, which we like, but there's a chance of computation repeating itself because of how it's structured, which is a bad situation. It's not good if you have expensive code in these blocks. It also limits what monadic effects can happen when accessing shared memory. And our goal is to then use this to implement a concurrent hash table using this approach I talked about earlier. So we've implemented an STM library, defined the interface, implemented a hash table with it, and have extracted it already to C++. We have yet to do the verification, but we intend to do so. And quickly, what do we mean by safely? So one thing to make very clear, we have not proven this correct, and we do not plan to. Instead, we plan on using more lightweight methods, such as differential testing our extractor to others that are verified. And also, all of our generated code will undergo the same testing as handwritten code would in production. But this gives us a lot more flexibility to kind of generate code that is useful and kind of acceptable to the engineers that we're working with. And so as future work, We have a lot of things we want to do, including supporting more of Rocq, because right now we don't support co-inductive, some of the more complex dependent inductive types. We're midway through implementing modules and some other things. We want to definitely improve the runtime efficiency of extracted code without sacrificing readability too much, which is a bit of a challenge. So our current thought is to do CPS conversion and defunctionalization as a kind of happy middle ground. We'll see how that goes. And in the end, we would love if our extracted code generally runs faster in C++ than using OCaml extraction. So, we'll see if that actually happens, but that's our goal. And also, we want to actually verify code that gets into production at Bloomberg, because that'd be pretty exciting. And so, again, Crane is an extractor from Rocq to C++. It's functional style, memory safe, thread safe, readable. And it's not verified, but we're still doing things to ensure its correctness as much as possible. And yeah, we're trying to get it in production, do concurrent stuff. So thanks for listening.
Time for one quick question as Gregory gets set up.
Hi. Great talk, enjoyed it. I wanted to ask, we have the same problem with other kinds of generated code. Once you put your generated code into C++ and now you want to maintain it, how do you do that?
That would be a good thing to talk to you about. I don't have any particular thoughts. I mean, you could change it in Rocq, obviously, and then regenerate it. But
if you did it by hand, mightn't you introduce a bug?
Indeed, that would be a concern, which is why changing it in Rocq would guarantee it, but you'd also have to change proofs. Yeah, it's not so straightforward, but stuff we're looking to solve.
Happy to work with you.
Thanks.